everyone, it's calculating equilibrium type 4 time. This one is called the 100 rule, and so if you weren't too keen on the quadratic, then you might prefer this version of things. The 100 rule is a way of simplifying the math, which is fantastic, but it can only be used if we have a really small k. A small k means that we have very few products. So if we think about k is equal to concentration of products over concentration of reactants at equilibrium, a very small k means that at equilibrium we have lots of reactants, not very many products. So it's only when we have a small k that we can actually use this particular assumption method. And basically we're going to make an assumption, so it's not going to be completely accurate, but we're going to make sure that our math is within a 5% range of error. So I'll take you through the steps and we'll see how it works. We're going to jump right into an example and then we'll look at the steps individually. So at 20,000 degrees Celsius, K is 6.40 times 10 to the negative 7. As you can see right off the bat, that is a very tiny K. And again, that's what we need in order to be able to do a 100 rule. I would say the lowest or the highest K value would be probably something times 10 to the negative 5 before it doesn't work anymore, but there's some steps within the process that will allow you to know whether a 100 rule approach is going to work or not, so that will be helpful. So there's our K. We're decomposing CO2 into CO and O2, and we want to calculate the concentrations of all entities at equilibrium if 0.25 moles of CO2 is placed into a 1 liter container and then it's heated, etc. We're also going to practice this percent reaction calculation again because we can actually do percent reaction calculations with any of the types. Type 2 is a little bit tricky because if we start with products, which we often do, we can't really do it for that, but a type 1, a type 3, and a type 4, we can do percent reactions. I don't think we practiced any with type 3, but we could have done those. So as always, our approach is going to be our ICE table. So all 4 methods start the same way. You do your ICE table, you read the word problem, and from the word problem you get your I. So we're going to take our 0.25 moles per liter, moles divided by 1 liter gives us 0.250 moles per liter. Doesn't tell us we have any product, so again, this is a nice easy C. We have to shift towards the zeros, so minus 2x plus 2x plus x, I plus c equals E, 2.5 minus 2x, and x. From here, just like in a type 2 and 3, our approach is going to be using the K. So we're going to set up a generic K first, and then I'll substitute. So K is the concentration of the products. Coefficients become exponents. That's probably the most common thing that's done incorrectly here, is forgetting those exponents. And then in the next line, we can substitute. So we've got 6.40 times 10 to the negative 7 for K. Inside the first bracket, we've got 2x, don't forget your squared, and then the second bracket, we've got x, and then along the bottom, we've got 0.250 minus 2x, all squared. As you can see, this math is pretty complicated, and this is why we're going to use a simplification method. I'm going to do one more simplification first, and that is to just combine everything on the top here, and then we'll look at how do you simplify even further. So at the top, I took my 2x, it was squared, so it becomes 4x squared, times another x, that's now 4x cubed. And again, I'm going to keep it in this form. You can see that this is a pretty tricky problem because I've got a cube term. The denominator, I'd have to expand, collect like terms, cross multiply, etc. And if I don't have that quadratic formula, squared, x, and number, then I can't really use quadratic, and I can't take a square root of both sides here. So again, a type 2 is not going to work. So this is where a type 3 is going to come in handy. So there's some steps to the type 3, and I'm going to put those in red for us, or orange for us. So the first step is to make an assumption. And the assumption is always about the denominator. So we're going to assume, since K is small, that 0.250 minus 2x is going to be approximately equal to 0.250. We're basically saying with this statement that we think x is so small, it's not going to make a difference. And we're basing this on the fact that k is so small, and as we looked at in the very beginning of our lesson, a really small k means we have hardly any products, which means the shift, that x in our ICE table, has to be pretty small. So this is the first part of the 100 rules to make this assumption. Now, before we keep going, we're going to check our assumption, and this is where this process gets the name 100 rule. So what we do is we do the assumed concentration, we use square brackets for concentration, divided by k, and this must be much greater than 100 in order to proceed. So I'm not going to put my values in, and let's see what we get. So we get 0.250, that's the value I'm assuming, it's up here. And we're dividing it by k, 6.40 times 10 to the negative 7. And then we're going to see what value we get. Now, I just put it into my calculator. I'm not going to write down all those numbers. But what I can see is that it's much greater than 100, which means, therefore, my assumption is warranted, we say. This just means that the assumption is going to work or should work, so keep going, use the assumption. If I got a value around 100 or less here, then I would stop immediately and I would look at the fact that it's probably a quadratic or a perfect square, and so I would abandon this process. So that's what I do here. I make my assumption, I check my assumption, and that allows me to either keep going or to abandon ship. So although those two things that we have to do are a bit of a pain, have a look at what we've now been able to do with the math. We put 0.250 minus 2x, we've now replaced it with just 0.25. So the math is really simple. I'm going to have to square the 0.25, cross multiply, divide by 4, and then take a cubed root here. But this math is much more doable than the math before this. So I'm just going to give you the value here. You should be able to sort this out for yourself, but you should get an x value of 2.15 times 10 to the negative 3. You don't have to keep into scientific notation here, but I've just done that for us. So we have one more step for 100 rule that, again, is sort of part of the process of allowing us to take terrible math and make it easy, and that's something called the 5% rule. Again, I'm going to put it in orange here, 5% rule. So the 5% rule, we have to take the assumed value minus the actual value, which we don't have at the moment, but we'll get it in a second, divided by the assumed value, times 100%. And when we do this, we need to get a value that's equal to or less than 5%. This is the amount of error that we have by making this assumption. And so this 5% rule just makes sure that the assumption that we're making is less than 5% error. So I'm going to work out the actual value at this point, and the actual value means I go back to this assumption. This is the assumption statement that I made, and so if I want the actual value now, I'm going to replace the x with the number I just found and figure out what it actually is. So I'm going to take the 0.250 minus 2, and then I'm going to put in that x that I just found, times 10 to the negative 3. And then I'm going to figure out what this value is. That's the actual value. You can do this all in one big equation, or you can do it separately like I'm doing here. All right, so now that we've got all our values, let's plug it into our 100 rule. So our 5% rule. So our assumed value, again, going back to the assumption, we assumed that our value there was 0.25. So that's the assumed value, 0.250. The actual value I did up above, so it's a 0.246 times 100. And we usually consider this to be an absolute value because it doesn't really matter if you're higher than or less than the actual answer. We just have to make sure there's no more than 5% error. So when I do this calculation, I get 1.6%, which is less than 5%. Therefore, the assumption, we say, is valid, meaning what we did was good. All right, so the last step is just to use that x value that we found out and confirmed that it was good and put it into the E part of the ICE table to solve for all the values. Our first one is the concentration of CO2, and that is actually exactly what we did to find the actual value. So I'm just copying it out because we've already done this work. We can do it from scratch, but if you recognize you've already done it, it makes life a little bit easier. We also have CO, which is 2x, so 2 times 2.15 times 10 to the negative 3, and I'm getting 4.30 times 10 to the negative 3 there. And lastly, my O2 is just x, so 2.15 times 10 to the negative 3 there. And that is it. So these are our steps for solving. So the first step is you're completing your ice table. Then step 2 is set up your K. Step 3 is to make that assumption statement about the denominator. So I've done it in red here for you. This is what it looks like. Since K is very small, assume that blank equals blank. So those numbers you're going to put in yourself. It'll change every time you do a problem. Number 4, you're checking your assumption using that 100 rule. So that, remember, that's the assumed concentration divided by the K, and it has to be much greater than 100% here. I'm going to put that in, much greater than 100. And then we make a statement that says, therefore, the assumption is warranted. If you can't remember the word warranted, just put the word good. That'll do. Then in step 5, you're going to insert the assumed value and solve for x. That's where the math gets nice and easy. And then you're going to do that 5% rule. So again, assumed minus actual divided by assumed times 100. Again, I'm going to put in those absolute values because it doesn't matter for plus or minus. We just want the actual numerical value here. And again, if we can't remember the word valid, that's fine. Use the word good. It just means that, yeah, the math we did, it's okay. Number 7 is you're going to take that x value now that we've confirmed it's good and calculate all the values at equilibrium. So I just realized that we forgot the percent reaction, and I added another slide, but it just duplicated my old slide, so now we're kind of stuck. Tell you what, we're going to do the 5% rule because I think it's important to practice it, but I'm going to have to squeeze it in over here. I can't blank this screen for some reason. So let's just do it over here. It's going to look ghetto, but whatevs. So percent reaction, remember, is always in terms of products, and if we go back to that equilibrium equation from the question we just did, I've just put everything down here. Again, the ghetto continues. And we start with 0.250 in the I part of our ice table. We have the concentration of both products at equilibrium from the first part of this question. But if I want to focus on one of the products, the one that makes more sense is going to be the CO, and that's because they're both a 2-to-2 relationship. That makes the stoichiometry easy, because if I have 0.25, I should be able to get 0.25. Because the numbers are equal, for coefficients, the actual concentrations are also going to be equal. So that's why I chose that value there, which means when I'm choosing the concentration at equilibrium, I'm also going to be choosing the CO. All right, so up at the top here, again, nice and squishy. I'm doing a great job. We have the value of the CO at equilibrium is 4.3 times 10 to the negative 3. We did our stoich. The value with stoich would be 0.25. And the percent reaction is 1.72%. 1.72% is the percent of products in the container at equilibrium. It's terrible. Just like we said in the beginning, in order to do a 100 rule, you have to have a really small k, and really small k means you have hardly any products, which is why we're allowed to use this assumption in the first place. This just proves it even more. This is showing us that we do have a significantly tiny amount of products at equilibrium. Here's example number 2. I've just set up the ice table for you just to take out just to make it more practical so that you don't have to pull things out of a word problem. So we have H2O in equilibrium with H2 and O2, and you've been given 0.55 moles per liter of the water. What I want you to do, oh, and you also have a K value. K is 1.72 times 10 to the negative 11, so itty bitty. What I want you to do is pause the video, try this on your own. You'll notice there's a part B as well for calculating percent reaction. So I want you to try both of these parts. I would probably check at the end of the first part first, make sure you've got the right answer, and then go on to part B. But again, pause and see if you can do it on your own, because again, of course, that's what you're supposed to be able to do at the end of this lesson. So do it first, then check it, and then we'll have a look at the solution. So our solution, we start with our ice table. So we've got 0.55 moles per liter of the water. We have zeros in the ice table, which makes our life easy. We are going to shift to the right to reach equilibrium, because we can't have zeros. And I plus C makes E as always. So there is our setup. I'm going to put our K up here. Again, it's a really tiny K. We've got 1.72 times 10 to the negative 11. Just like the last time and just like in a type 2 and 3, my next step is to set up a K equation. I'm going to set up a generic K first, then substitute. So remember, K is concentration of products or reactants, and the coefficients become exponents. Now we can substitute. I'm also going to simplify the top line again, just like I did the last time. So, what's happening? Sorry, everyone, sorry. All right, I got a little too close to that arrow, I think. So, a couple fixes. You'll notice I put the brackets and the squared around the denominator, and now I've substituted, so I've simplified the top. 2x squared gives us 4x squared, times another x gives us 4x cubed. Sorry, that doesn't look like a cube. Ooh, that looks even worse. That looks even worse. Okay, cubed, perfect. And at this point, I've got ugly math, a small k, that lines us up perfectly for the 100 rule. So I'm going to start with my assumption. So I'm going to assume that my denominator, 0.55 minus 2x, is approximately equal to 0.55. You'll notice it's just what's inside the bracket, so I don't bring the squared with me. That stays behind. It's just what's inside the bracket that I'm going to be making. And I also want to say, since k is small, or very small. And you can reverse the language. You can say, since k is very small, assume that, but the two pieces need to be there. Now that I've made an assumption, I'm going to see if the assumption is going to work, so I'm going to do the 100 rule thing next. So the 100 rule, remember, I'm going to take the assumed value, 0.55, I'm going to divide it by k, and it must be much greater than 100. So I put it into my calculator. It is really big, so much, much greater than 100. And then I'm going to say, therefore, the assumption is warranted. Now again, if I had forgotten what to use there, I might just say assumption's good, and that's fine. So I'm now going to use my assumption. My denominator got really cleaned up, looks much better there. Don't forget the squared, because remember it's only the inside bracket that I've changed, so the outside bracket, the squared, is still there. Let's solve for x. So you're going to square, rearrange, etc. You should be able to get 1.1 times 10 to the negative 4 here, I believe. And now we have one more piece of the 100 rule, and that is our 5% rule. All right, so our x is 1.1 times 10 to the negative 4. We're going to set up our 5% rule. So our 5% rule is the assumed value, 0.55 on top and bottom, minus the actual value. So I've just written in yellow here that assumption statement again. And here I've just substituted it in directly. So you can do it like this, or you can do it separately and then substitute it in. It doesn't really matter. I'm getting a very small value of 0.04%, which is much less than 5%. Therefore, my assumption is valid. Yay, it means it's good. So the last step then is to plug the x value that I found into the values at equilibrium. So I've just substituted in the x value along the bottom. Again, that's just putting our x into the E row of the ice table, and I've got those three values. So next I'm going to do that percent reaction again. So I've just copied over the I part of the ice table here because that's what we need for the stoic part, which is the denominator of our percent reaction. And again, I'm going to choose one of the products. It doesn't really matter. I've proved to you before that in our type 1 lesson that you can choose either of the products and it'll come out to be the same percentage, but there's typically one that's easier to do than the others. And the easy one here is you've got a 2 and a 2 for coefficients, which means 2 to 2 is the same as 1 to 1. So you could, if you had a one-way arrow, you should be able to get 0.55 H2. So that means I'm going to use the H2 values for my percent reaction. So the top value, remember, is the H2 at equilibrium. So that's my 2.2 times 10 to the negative 4. And then my equilibrium value is 0.55 times 100%. And let's see what we get. And we get a tiny, tiny number, 0.040% product at equilibrium. Hardly any product. Again, this just reinforces that making a 100 rule assumption is a good idea. I've got one more for you to try if you want. It's optional. If you're feeling good, you can go on to our homework questions. And we've got a few questions to try using our 100 rule. 100 rule is a really handy approach. We're actually going to see it again as well because, like I said, it simplifies the math. And if you can do it, why not?